When you look up at the night sky, the light you see can be millions, if not billions, of years old. That's because the astronomical objects we perceive with our eyes are so far away that light, which travels at a finite rate, takes a long time to reach Earth. So really, when we look up into the sky, we're actually looking into the past. In astronomy, we measure how far back into the past we look by using a quantity called redshift, a color displacement that relies on the evolution of the energy density in the universe. For scale, the present time is at redshift 0, while a redshift of 12 corresponds to about 370 million years after the Big Bang. When we want to study the evolution of the universe, we can use telescopes to look at different redshift ranges in order to obtain information about how stars, galaxies, and the universe itself have changed over the past several billion years. However, our telescopes are too weak to see most objects from about redshift 9 or above, which corresponds to around 550 million years after the Big Bang or earlier. That's because objects from this time are so faint that they are incredibly difficult to detect with any modern equipment. This makes it hard to study the early stages of evolution for many objects, like galaxies, since we don't have enough information about their properties at these high redshifts. Fortunately, the universe has given us a series of natural cosmic telescopes that my project aims to use in order to find larger numbers of high redshift galaxies. What are these telescopes, you may ask? Galaxy clusters. Einstein's theory of general relativity predicts that large quantities of mass are capable of bending space. In my case, galaxy clusters, which are equivalent to around 100 Milky Ways all moving around together as one gravitationally bound unit, are large enough that they bend space to distort the light emitted from background sources in a process called gravitational lensing. This distortion of light helpfully magnifies background sources, which also makes them brighter. As a result, we can use galaxy clusters to discover previously invisible objects in the universe. As a part of the reionization lensing cluster survey, my thesis focuses on modeling several galaxy clusters with similar properties in order to quantify their magnification effects on background sources. Since the magnification of the cluster is dependent on mass, I will apply gravitational lensing techniques to generate a mass profile for each cluster, which includes both the visible matter distribution and the dark matter distribution of the cluster. I will then create a model of the magnification of each cluster, which we will use to determine whether high redshift galaxy candidates are actually in the redshift ranges we are targeting. My thesis will thus give us the tools we need to start filling in some missing pieces about the evolution of galaxies at the beginning of the universe.